Hello, my name is Yusuf Khan and I'm doing a little review of a combustion type problem. This problem in particular is going to come from chapter 3 of Tro's textbook, number 130 from the problems at the end of the chapter. So let's go ahead and jump in. I've gone ahead and written this problem out. Not exactly how it was in the book, but pretty close. And here's the problem. So we had a substance containing unknown quantities of carbon, hydrogen, and oxygen. We combusted it. We just didn't like it very much, so we burned it. That sample initially contained 1.893 grams of this mystery substance. We do know, like I just said, there's carbon, hydrogen, and oxygen inside the substance. We're also given this piece of data that it has a molar mass of 270.36 grams. And as with most combustions, this problem yielded 5.545 grams of carbon dioxide and 1.388 grams of water. Now, it's not typical that a combustion problem yields that exact mass of carbon dioxide and that other mass of water, but the general formula is this. You've got this substance, and it can contain oxygen, it often does, and it reacts to form some water and some carbon dioxide. Well, you might notice that I've suspiciously left a little blank here, and that's because there's one more part of combustion that usually occurs. And I suppose before I get any farther, let me go ahead and make note of the fact that we don't know how many moles of this substance we have. So we don't know how much carbon we have, or hydrogen, or for that matter, the oxygen. Now, in terms of balancing this chemical equation, we can't consider this. When you are burning a substance, there's one more ingredient that must be present. Yes, something has to be flammable, but if you think of the example of a birthday cake and you have a friend, you want to light the candles on fire, you want some combustion to occur. Well, if you were on Mars, where there's no oxygen in the atmosphere, you'd have a very sad birthday indeed, because not only would your candles not light, but the breath that you just taken to blow out the candles that you'd hoped would light would be pulled out of your lungs due to the pressure differences. But that's getting to the next unit, and that would be a really sad birthday. Anyways, my point being, oxygen is also required, oxygen gas. For any type of combustion, we're going to need oxygen gas in addition to our flammable substance. Now, for this problem, our end goal is going to be to find the molecular formula of our unknown compound. Instead of these question marks, we're going to want actual numbers. And also, we're going to learn the distinction between a molecular formula and the empirical formula, which is a simplified version of that molecular formula. So let's go ahead and get started. What we're going to look at is these products to start with. As I said, this is not a balanced chemical equation, but if you look closely, oxygen is present in all of these compounds, and that's going to be a problem. If we're looking at oxygen, we're not really going to get very far here. But take a look at these two things. That's hydrogen. And whatever we get as a product had to be present as a reactant. So where could this hydrogen have come from? Well, hopefully you can see that there's only one place where hydrogen could have come from here. And it had to come from our initial substance. As I said, oxygen isn't going to get us very far, but what about carbon? As far as products go, all of our carbon is present in this particular product, and all of it must have come from our unknown substance. So we can go ahead and draw a little rectangle thing over there, and a rectangle over there indicating this connection. All of the carbon in the products must have come from this reactant. So now we have a connection. When we first look at this problem, maybe we see a bunch of disparate pieces and we don't know how to put it together, but now we have some connections that we can go ahead and pursue. So let's do that. We said we had 5.545 grams of carbon dioxide. Well, let's go ahead and work with that. All of that carbon that we have there has come from this compound we started with. So what we're going to do is use this 5.545 grams of carbon dioxide and find out how many moles of carbon are present there. That number of moles of carbon will be the same number of moles that are present inside of our compound. So how do we actually do this math? Well, it's going to look something like this. We're going to use the molar mass of this carbon dioxide to find how many moles of carbon dioxide we have. I found out earlier that 44.01 grams corresponds to 1 mole of carbon dioxide. And I'm going to go one step further here instead of just stopping at moles of carbon dioxide, because I'm not actually concerned with that. What I do want to know is carbon. There's a very simple molar ratio. Well, I guess that's not a term we should use. There's a very simple relationship. We can see that in 1 mole of CO2, there's 1 mole of carbon. So I'll write that down. 1 mole of CO2 corresponds to 1 mole of carbon. And so we can go ahead and solve this. If you punch this into your calculator, you should find 0.1260 moles of carbon. Awesome. Now we're making some progress. Let's do the same for water. We initially had 1.388 grams of water, and what we're going to do here is convert that to moles of hydrogen. So the molarity of water, which we will become increasingly familiar with as time goes forward, is 18.02 grams for every 1 mole. 1 mole of water, that is, and I should go ahead and be specific. And I'm going to take this one step further because I'm not actually interested in just water. When I look at a mole of water, I notice that for every 1 mole of water, hey, there's a 2 down here. That means that there's actually 2 moles of hydrogen. I'll punch that into my calculator and find that I have 0.1541 moles of hydrogen. All right, so I've done some really good stuff here. I found 2 mole values for our actual compound, and I can fill these values in to my formula. There's going to be some problems with that, but we'll get to those in a moment. So I could say I have C.1260, and I have hydrogen 0.1541, and I don't know my oxygen. Now, by now in chemistry, you've hopefully noticed that none of our chemical formulas have decimals like this, and that's going to be a problem that we're going to need to address. For now, however, we're going to go ahead and realize that once we find a value of oxygen to put in here, these will be all related by the same ratio, and we can use that moving forward. Now, let's shift gears here, because if we look back at our problem, we've kind of hit a dead end. We've used a couple of our pieces of data. We've used this piece of data. We've used this piece of data. And we have a couple left. We have an overall mass of this substance. That's what we're going to look at next. And we have a molar mass that's just sort of sticking out like a sore thumb. What are we supposed to do with that? Well, we'll find out in just a moment. So as far as the mass goes, hopefully you'll agree with me that this is true. We have a certain sample mass, and we can go ahead and fill in right now that that mass was 1.893 grams. We know that this substance is made up of carbon, hydrogen, and oxygen. So if we find the mass of carbon that makes up this substance and the mass of hydrogen that makes up this substance, we can fill them in here and here, leaving us only with a leftover mass of oxygen. So the trick is going to be to find the mass of each of these substances. Again, hopefully this makes sense. In any sample of this substance, it's going to have the same ratio of carbon, hydrogen, and oxygen. So if we subtract out the mass given from carbon and from hydrogen, all that will be left is oxygen. So let's go ahead and do that. How will we do that, you ask? Well, we have a couple of values that we just found for how many or how much of carbon and hydrogen we had. For carbon, we said we had 0.1260 moles of carbon. And for hydrogen, we said we had 0.1541 moles of hydrogen. To get from moles of an element to its mass is not too difficult. All we're going to have to do is get the molar mass of our given element. For carbon, we're going to put 1 mole on the bottom. And by the way, this is sometimes known as the railroad tracks method. My goal is to cancel my units so that I'm left with units that I like. In this case, those units are going to be grams. So we're going to have 12.01 grams over here. And over here, we're going to say 1 mole of hydrogen corresponds to 1.008 grams. All right, so we can go ahead and plug this into our calculator. If we do that, we will find values that we can subtract out. We should find 1.513 grams of carbon. We should also find only 0.1553 grams of hydrogen. And now I realize that wasn't on the screen. There you are. Now we have two masses. These are the amounts of mass of the sample that were taken up by things besides oxygen. So let's go and plug these into that equation we had up above. We will say for our mass of carbon, we found we had 1.513 grams. And for our mass of hydrogen, we had 0.1553 grams. Left over is going to be our mass of oxygen. So let's subtract this out. We're going to subtract 1.513 from both sides and 0.1553 from both sides. The leftover mass is going to belong to oxygen. The mass of oxygen that we find comes to about 0.225 grams of oxygen. Yeah, go us. We are getting closer to the finish line. Now, let's go back to our other page. We found out that this should be the ratio of each of these substances. Can we fill in 0.225 over here? Hopefully your answer is no, because remember, these relate to mole values, not to masses. Our final step with this oxygen in particular is going to be going from 0.225 grams of oxygen and converting that to moles. The molar mass of oxygen is 16 grams per mole, so if we plug this into our calculator, we should find a value for how many moles of oxygen we have. And actually, we don't have many. We only have 0.0141 moles of oxygen. So now finally, instead of having a question mark here, we can put in a value. This is great. So I'll just go ahead and scribble that out and say 0.0141. Now the thing about this type of ratio is that this is basically a pain to say. Technically, this is the right ratio, but in reality, we don't have 0.0141 oxygen atoms. That doesn't make really any sense. So we have a fairly simple strategy that we're going to use here. What we need to do is get whole numbers. So if you try to think of a way to turn these into whole numbers, there are, I'm sure, a few strategies, but the easiest one is to divide each of these numbers by the smallest number. The general formula I'll write down here for you. You take your number of moles of whichever of those you like and divide it by the smallest number of moles. For us, that's going to mean we're dividing our number of moles by our smallest, which is 0.0141 moles. And again, that corresponds to our oxygen. So we do this, and we come up with, finally, our empirical formula. That's very close to the finish line. And let's see, where exactly do we have our empirical formula? It comes out to something like this. So I divided my 0.1260 for carbon by 0.0141, and I did that with hydrogen and oxygen too, and I came up with this formula. C9H11O. This is my empirical formula. So what is an empirical formula? Are we done? Let's go back to the problem. And, oh, molecular formula. Well, that sounds pretty close to the same thing, right? Yeah, right, it's pretty close, but not close enough. Let's finish the problem. So here's the definition of an empirical formula. The empirical formula. It's the simplest ratio of elements in a compound. And note, it may not actually represent the formula you have. In this case, I'll tell you, it doesn't. So if this is our empirical formula, C9H11O, well, the actual formula could potentially be a multiple of that. It could be C27H33O3. Notice how I just multiplied everything by 3. This would be an example of a molecular formula. Only empirical formulas are simplified so that you can't divide out any more numbers. Just as one more quick example, this could be a really crazy compound, C90H110O10. Notice that I've just multiplied our quantity by 10 for each of these. So what are we going to do? How do we get to the end of this problem, to the molecular formula? Well, we had one last piece of data that was on this problem page, and it's right over here, a molar mass of 270.36 grams. Now, I'm sure you could come up with all sorts of creative things to do with this, but if you have this type of problem, save your molar mass till the very end. So the actual molar mass of our compound, our true compound, is 270.36 grams. So I'll write that here. Molar mass is equal to 270.36 grams. Well, by contrast, we have this empirical formula, C9H11O. What we can do is we can find the formula mass, or the empirical formula mass, and compare it to this molar mass. If we do that, we should find a molar mass corresponding to C9H11O. And that molar mass for this guy is going to be 135.2 grams per mole. If you look at this closely, you might notice a relationship between our empirical formula mass and our molar mass. In fact, they pretty closely seem to be, well, this empirical formula mass is clearly half of this molar mass. So the general formula you're going to use, or at least one that you can use, is your molar mass divided by your empirical formula mass will give you what we can call N. In this case, if you divide 270.36 divided by 135.2, you should find N is equal to 2. And if N is equal to 2, that means that the factor you multiply your empirical formula by is 2. So I kind of conspicuously skipped multiplying this by 2 above. I multiplied by 3 instead, but it turns out N is equal to 2. So to find my actual formula, all I have to do is multiply by 2. So instead of C9H11O, I'll multiply each of those numbers of particles by 1, giving us C18, H22O2. And that, my friends, is the formula of the compound. Now, if you have any questions about how I went through this, about my process, or anything, feel free to leave it in the comments below, and I will get back to you in as timely fashion as I can. This goes through both combustion and empirical formulas, and this concept of empirical formulas also applies to percent composition problems. So be aware that in the recitation manual you may have gone over a problem that dealt with percent composition, such as I have 40% oxygen, 30% carbon, 30% hydrogen, something like that, and you would have found an empirical formula. That empirical formula, again, is not necessarily your molecular formula. So to find your molecular formula, go through this final step, find the value of N, and do N times your empirical formula to find the actual molecular formula. All right, thanks very much for watching, guys, and I hope this helped you out. See you later.